Welcome back. Having introduced the two-dimensional continuous Fourier transform of a discrete two-dimensional signal in the previous segment, we can now describe and understand the operation of sampling. That is, the operation of turning a continuous signal into a discrete one. As we discussed during the first week of class, sampling is needed in being able to bring a continuous signal into the discrete world so that it is processed by a computer. In most cases, we are also interested in bringing the discrete signal back to the continuous world so that we can see it or so that we are able to hear it. A fundamental question, therefore, when sampling is performed is under what conditions can we move back and forth between the continuous and discrete worlds without loss of information, or under what conditions we can reconstruct the continuous signal from its samples. We derive these conditions, which are referred to as the Nyquist theorem. A band-limited signal can be reconstructed from its samples if it is sampled with frequency at least twice as large as the highest frequency in the signal in each dimension. We derive the theorem in 2D. However, it's a straightforward extension of the 1D sampling theorem, and it can also be extended in a similar way to dimensions higher than 2. Actually, in 2 and higher dimensions, there is more freedom in performing periodic sampling. We'll only cover here rectangular periodic sampling, but one could use, for example, hexagonal periodic sampling in 2D. Sampling provides the intuition in understanding what happens when we sample now the continuous Fourier domain. It leads to the definition of the discrete Fourier series and also the definition of the discrete Fourier transform, which is the topic of the next segment. So let us now have a closer look at this exciting material.
One of the important concepts in digital signal processing is the concept of sampling. It connects the analog to the discrete world. It's true that with the proliferation of digital sensors, there is less of a need for converting an analog image to a digital one, but the mathematical concepts of sampling are important for understanding other topics in image and video processing. They're important, for example, in allowing us to understand the steps we need to take in changing the sampling rate in the digital domain. For example, when we upsample or downsample an image, as we'll see later. So assume that we have an analog image like the one shown here. Such an image can appear, for example, on a positive photographic film. I realize, of course, that for the younger people in the class, you may or may not be familiar with negative or positive films. It is, however, worthwhile continuing with this topic. I can represent this signal in the frequency domain, and here is the spectrum of the analog signal, x of a, omega 1, omega 2. What we show here is really the region of support of the spectrum and not the shape of the spectrum itself, but it's not relevant, the shape, for the discussion that follows. I want now to represent this image by discrete samples. So I superimpose a grid as shown here and only keep the values of the image at the grid points. So the digital image I end up with is the one shown here, and there are two parameters that control this grid: the spacing in this direction, T1, and the spacing in the vertical direction, T2, and these are referred to as the sampling periods. I can now represent this discrete signal in the frequency domain. I can take the Fourier transform of this signal as we've done already in this class. And if I find the spectrum, it looks like this. It's no surprise that it's periodic, because we do know that the spectrum of a discrete signal is periodic, a property that we covered in quite some detail. And it is formed really by performing the periodic extension of the spectrum of the analog signal, again, as shown here. The mathematical expression to describe this is the one shown here. So far we've been using this notation, omega 1, little omega 1, omega 2, to denote the Fourier transform of a discrete signal. And this is exactly what this is, since omega 1 is the normalized frequency and equals big omega 1 times T1. So omega 1 is in radians, while big omega 1 is in radians per unit distance, spatial distance, let's say millimeters as an example. And T2 is also in millimeters, so the units, the dimensions really match. And of course, omega 2 is given by a similar expression. So what this expression tells me again is that I take the spectrum of the analog signal and I periodically extend it. So K1 ranges from minus infinity to infinity, so is K2. And the periodic extension in the horizontal direction is with respect to 2 pi over T1, while in the vertical direction with respect to 2 pi over T2. So this point here is 2 pi over T1, while this point is 2 pi over T2. So we see that in performing sampling, there are two important parameters, the sampling periods, T1, T2. They control the spacing of the points in the spatial domain, and they also control how far apart the replicas of the analog spectrum in this periodic extension are going to be located. We say that an analog image is critically sampled if I use the appropriate T1, T2 here, sampling periods, so that when I find now the Fourier transform of the discrete signal, which is formed by the periodic extension of the spectrum of the analog signal, the spectra here just touch next to each other without overlapping. And in this case, at least mathematically speaking, I can filter the baseband of the spectrum of the discrete signal, and then this will give me back the spectrum of the analog signal. Therefore, I'll be able to go from the discrete world back to the continuous world without losing any information. If I use a smaller T1, T2 sampling periods than in the previous case, then when I look at the spectrum of the discrete signal, it's going to look like this. And in this case, I've used more samples than I needed to represent accurately the continuous image. I have oversampled. If I go the other direction and use sampling periods here, T1, T2, which are greater than the periods used for critical sampling, then if I look at the spectrum of the discrete image, it looks like this. When I do the periodic extension, one replica overlaps with another replica, and this phenomenon is referred to as aliasing, which means that the high frequencies here alias themselves as low frequencies. They use a false identity. And in this case, it's not possible to recover the original signal. I am not able to untangle the low and high frequencies that have been mixed up. In performing sampling, an important question is what should the sampling periods T1 and T2 be equal to, so that I'm able to go back from the discrete samples to the analog image. Intuitively, one should expect that how close together the samples are should be a function of the spatial frequency in an image. If the image intensity varies a lot and rapidly, which means that there's a lot of high frequency energy, then intuitively one should use samples that are close together so that all these fast variations of intensity are captured appropriately. If on the other hand they have a rather flat image, then a few samples will suffice. And this is exactly what the Nyquist theorem tells us. So here is again the support of the spectrum of the analog image, and let's call omega n1 the highest frequency in the horizontal direction and omega n2 the highest frequency in the vertical direction. After I sample this image, the spectrum of the discrete image is desirable that it looks like this. So in other words, there is no aliasing. So this point is 2 pi over T1, and therefore the point in here is 2 pi t1 minus omega n1. So clearly, as long as the ordering of these 2 points is as shown here, so as long as 2 pi over t1 minus omega n1 is greater equal than omega n1, there is no aliasing in the horizontal direction, and this gives us the condition that the sampling frequency should be at least twice as high as the highest frequency in the image, and I can obtain the similar condition in the vertical direction. So the sampling frequency in the vertical direction should be greater or equal than omega n2. So if these two conditions are satisfied, then I can recover the analog image from the discrete one by using a low-pass filter as shown here. So this low-pass filter, let's say f omega 1 omega 2 should be equal to t1 t2 as long as omega 1 is less than pi over t1 and omega 2 less than pi over t2 and 0 otherwise. This t1 t2 gain is here because if you look back, if you slide back at the relationship between the spectrum of the discrete signal and the analog signal, there is 1 over t1 t2 factor there. So I need this gain to bring back the signal at its original values. So these frequencies, this is for example minus pi over t1, this is pi over t2, so this is the filter that is shown exactly here. So in summary, what the Nyquist theorem is telling me is that if I have a band-limited analog signal, I can sample it with frequencies that satisfy these conditions, and then I can recover the analog signal from the discrete one using a filter like this in the frequency domain. And what this means in the spatial domain is that I perform band-limited interpolation with a kernel which is the inverse Fourier transform of this ideal low-pass filter, and this is a two-dimensional sinc function, a sin x over x function. In illustrating the concept of sampling, oversampling, undersampling, let us consider a simple one-dimensional signal, the cosine depicted here. It has frequency equal to 0.9 Hertz, or in omega units 2 pi f, 1.8 pi radians per second. So in a 10-second interval shown here, there are 9 cycles of this particular cosine. If I take the one-dimensional continuous Fourier transform of this signal, I see that its spectrum looks like this. It consists of 2 impulses at 1.8 pi minus 1.8 pi, and clearly this tells me that there is only one frequency present in this signal. It's therefore a pure tone. Now the Nyquist frequency for this signal, it's either 1.8 Hertz or 2 pi times 1.8 radians per second. So here with the green samples, we show the sampled version of this cosine when we greatly oversample. If you recall from the previous slide, the omega Nyquist, that we denote it like this, was 1.8 times 2 pi radians per second, so 3.6 pi rads per second. So instead of using the Nyquist, I use a 60 pi rads per second, or the sampling period is 1/30th of a second. So therefore I have 30 samples per second. There are 10 seconds in this interval, so there are 300 samples shown here. So if I look at the spectrum of this signal, then, as we know, we take the spectrum of the analog signal, these two impulses, and periodically extend it with period 60 pi. So I have one replica here at 60 pi, another at minus 60 pi, and so on and so forth. And in this case, I can go back and forth between the continuous and the discrete worlds by just using a low-pass filter, pulling out these two impulses, and in the time domain, I'm going to get the continuous cosine signal that I started with. I sample now my analog cosine I'm working with period 1 second, or frequency 1 hertz, or in omega with 2 pi radians per second. Recall that the Nyquist for this signal, omega van, is 3.6 pi radians per second. So with this sampling period, in this interval of 10 seconds, I have 11 actually samples, since I also sample at t equals 0. Let's see how this sampled signal looks in the frequency domain. Here is the spectrum of the analog signal, and I know that the sample signal has a spectrum which is the periodic extension of this spectrum with periods 2 pi. So here is the first replica of the spectrum, a second replica, and so on and so forth. So clearly, this high frequency component in the original signal aliases itself as a low frequency component. So when I reconstruct this alias signal using the low-pass filter shown here, I end up reconstructing the signal shown here on the left with frequency 0.1 hertz or 1 cycle in this 10-second interval I'm studying. You can look at this signal, also the one that results from the first sampled signal, where I had oversampled. I had 300 samples there in this interval, and if I downsample by a factor of 30, so I throw away 30 samples, I keep one, throw away 30, and so on, then this is the signal that we'll end up with. So we can either think of this signal here as resulting from the downsampling of the original analog signal, or downsampling the sample, the digital signal, right? So doing the downsampling in the discrete domain. We would like now to pictorially connect what we've learned so far and what is going to follow. I will not be showing any equations, since they can be found in any book on image processing or multidimensional digital signal processing. I think it's important to see what's the intuition behind the various concepts underlying the spatial and frequency domains, and just focus on the elements that are of primary importance in image processing. So we started with an analog image, such like the one shown here, which we represented also in the frequency domain. So here see the continuous spectrum of the continuous image in the big omega 1, omega 2 axis. And of course we show here just the region of support of the spectrum. So then we sampled this image, we superimposed this grid, and we kept the values at the grid points. And we also can represent, as we know by now, this discrete image in the frequency domain. We know by now that the Fourier transform of the discrete signal is periodic, and it's formed by the periodic extension of the spectrum of the analog image. I can represent the spectrum in the big omega 1, omega 2 domains, the continuous frequencies, or the normalized frequencies, little omega 1, omega 2. In going back and forth between the continuous and discrete worlds, I need to know the sampling periods or the sampling frequencies. If, however, all we are given is a discrete image or a two-dimensional array of numbers, we don't know what is the spatial distance between these numbers, between the pixels, and therefore I can only express the spatial frequency content in terms of the normalized continuous frequency, the little omega. And this is a material we've covered so far in the previous slides. Now, an interesting question that arises is what will happen in the spatial domain if I sample the Fourier transform of the discrete image. We saw before that sampling in the spatial domain results in periodic extension of the spectrum in the frequency domain. So our intuition tells us that the similar operation should take place now in the spatial domain, now that I'm sampling in the frequency domain. In other words, the image should be periodically extended. And this is exactly what happens, as we can show mathematically. So we see that a periodic discrete spectrum corresponds to a periodic discrete two-dimensional signal. Of course, the density of sampling in the frequency domain will determine the period in the periodic extension in the spatial domain. If I undersample in the frequency domain, aliasing will take place in the spatial domain. So we see that the discrete periodic signal has a discrete periodic representation in the frequency domain, and this is indeed the Fourier series going from here to here is the Fourier series representation. The discrete spectrum is often referred to as a line spectrum. Now, one period in the frequency domain corresponds to one period in the spatial domain, and in showing this here, I've chosen the sampling in the frequency domain to be done critically, so I have the same number of samples in one period in both the spatial and frequency domains. So we see here that an N1, let's say, by N2 period image corresponds to N1 and 2 samples in the frequency domain, and this mapping here is the discrete Fourier transform mapping that we will study next in quite some detail. So we see that if I have an N1 by N2 image, I can represent it uniquely by an N1 by N2 samples of the frequency domain of the spectrum of this image. So it's important to keep in mind that behind the DFT there are discrete periodic two-dimensional signals in both the spatial and frequency domain, since a number of the properties of the DFT can be derived and understood by considering these periodic extensions.